and I've been working with genetic diseases in various species since 1961. In about 1975, I started working almost exclusively on dogs, because although dogs bite, they're not nearly as bad as mink. and dogs are a lot nicer to pet. So I work almost exclusively on dogs now in my research work. My real interest is in the control of canine genetic disease. And I've been working with canine genetic diseases almost from the start of my career in 1961, although first I worked on mink and then cattle and then killer whales and a few other things. But my real interest is in dogs. And since about 1975 or 76, I've worked almost exclusively on dogs. So tonight, what we're going to do is start out on inbreeding. See the title. Most people kind of think inbreeding is not a very good thing to do. How many kind of feel that way? One? Anybody else? Most people kind of think inbreeding is detrimental. And so what they say they do is line breed. And line breed is a slow form of inbreeding, but it's still inbreeding. And so what I'm going to try to do is tell you what happens when you inbreed. And whether or not you should inbreed, you can make your own decision at some point in time. My opinion is that it's not, there's nothing wrong with inbreeding, even full brother-sister matings. But I'll let you make up your own mind. I'll give you the data to look at. By definition, inbreeding is any mating which is closer than an average or random mating within the breed. Anything closer than that. If you mate with a second cousin, then it's still inbreeding, but it's a slow form of inbreeding. As a generality, this would mean closer than a second cousin. The laws of most states say that you can't marry closer than second cousins. In some cases, you cannot marry, in some states, you can't marry closer than first cousin. But if you're in Arkansas, then the rules change a little. No, that's a joke. Actually, I don't intend to denigrate anybody from Arkansas. Remember, the important thing about remembering in inbreeding is that it does not cause mutations. Nothing can happen from inbreeding which is not already present within the dogs. The gene must already be there. There is no mutations caused by inbreeding. What it does is to make it more likely that a given gene that's already present will be expressed, will be shown by one of the offspring. It exposes defective genes. It does not cause mutations. Many people think inbreeding causes harm to the dogs in excess of what's already there. It's not true. If your goal as a breeder is to produce animals on a regular basis that win in your area of interest, whether it's conformation or agility or hunting or obedience or good pets or any other reason you use your animals, but if you wanted to win, if you want your dogs to consistently reproduce themselves, if you have a dog and you want to breed it so that the puppies come out looking like that dog or that mama, you must inbreed. That's the only way you will consistently reproduce a dog. That doesn't mean that you cannot breed a good dog by outcrossing. You can, but you will not consistently reproduce them. You will not establish a line. If you want to have a line of dogs, you must inbreed. In other words, in order to produce a breed of dog, or a breed in any other species, doesn't matter what it is, you had to inbreed. You're in the process of creating a breed. If you want that breed to look like itself, you must breed animals within that line. If you introduce stock from the outside, like this is still an open, your breed is still an open registry, still has an open registry, you will change the conformation of the dog based on what you bring in. That will happen. And once you bring in the stock that you want, and you want to consistently reproduce a set of animals that look alike, then you have to inbreed. Eventually, you will have to cut off outside dogs, or you will not produce a uniform animal, a breed, an animal that you can recognize as a Shiloh shepherd. At the present time, there are at least 308 breeds of dogs in the United States, at least that many. That's what I could count. Probably there's more. And over 500 breeds of dogs in the world total. And more are being developed right now, including you guys. I mean, until you stabilize your breed, until you cut off outside matings, you're still in a developmental stage. Nothing wrong with that, mind you. If you have a goal, if you want your dogs to look a certain way and you want to introduce new stock, that's fine. But at some point, if you want the dogs to reproduce, you have to cut off outside matings. In each and every case of all of those breeds, inbreeding was a technique that was essential to the development of the breed. Have you ever stopped to think why, if you breed two golden retrievers together, you never get a Labrador? Why is that? That's because in developing the breed, they excluded all Labrador characteristics. They inbred enough so that they shed all of the Labrador characteristics. And that's true of each breed. And that's why they say that they go through this bottleneck. This bottleneck is the period in which they're shedding outside groups of genes that influence the colors of the dogs, the size of the dog, the shape of the dog, the ear set, the tail set, all of the characteristics that make a dog. And, and some people, there's a guy that crosses soft-coated Wheaten Terriers and Portuguese water dogs to produce a dog that he calls a Huggy Bear. And he thought that if you cross a soft-coated Wheaten and a Portuguese water dog and get a Huggy Bear, then you cross the two Huggy Bears, they're all going to look alike. And they're not. They resegregate, and he gets a whole combination of dogs as they go out there. It's not a breed. He's not inbred them long enough to develop the characteristics of the Huggy Bear in a set of dogs. If you wish to develop a line of dogs within a breed, such as Mary's line or John's line, that is recognizable by a given characteristic, such as the ear set or the front or the top line or however your dogs are recognizable, you must inbreed. And you inbreed to fix that trait, that characteristic that you are establishing in your own line. You fix a trait by inbreeding. And if you don't inbreed, you will not produce enough recognizable animals to call it a line. It's just the way it is. Sorry, folks, but that's the way it is. I mean that's real. Inbreeding has been used throughout dogdom, and it's a technique. It's neither good nor bad. It's a technique. It's something that you use. If you see a set of dogs recognizable by a characteristic or a set of characteristics as belonging to or coming from a given breeder. Now, I don't know if you can do that in your lines. They're still in development, but are there recognizable sets of dogs now in Shilohs? Sure, okay. If you look at those lines, that set of dogs has to be inbred. It has to be inbred. Probably on the order of 30%, something like that. Yes. Yeah. Okay. Let's back up here. Those dogs are inbred. Is it bad that they're inbred? Not in my mind. I mean, not the way I think about inbreeding. It's not bad. Unless, of course, they're losers. And remember, if you breed losers, you're going to get a lot of losers. That's why most of us try not to breed them. Why bother? Remember, inbreeding fixes good traits and bad traits with equal effectiveness. You can't inbreed a dog and say, I'm only going to get the nice stuff, right? It'll split right down the line, 50-50 on the average. That's where you're at. You cannot inbreed ugly dogs without expecting to get a lot of ugly dogs. The ability to transmit a trait, either good or bad, uniformly is called prepotency. If the dog throws his own self, he's called prepotent. That's the name, if you want to get a little bit technical. Prepotency is based upon an individual's ability to transmit a uniform set of genes. And if you want to transmit a uniform set of genes, you need what's called homozygosity. And homozygosity is a big word to say that the two alleles for each gene are the same. All it means is that if you have a gene A and you want it to be homozygous, it has to be little a, or dominant A, dominant A. Both of them are the same. That's homozygosity. If you're heterozygous, the opposite word, then you have a little a and a big A as the pair. And that argument of having a big A and a little a together is the big argument against inbreeding. It's the only one that holds water, as far as I'm concerned. Okay. Homozygosity is produced by inbreeding. That's how you make an animal homozygous. And homozygous means that both members of a pair of alleles are identical, and they can be either recessive or they can be dominant. Little a, big A, big A. The term homozygous does not tell you which pair you have. It just tells you that you have a pair. The inbreeding coefficient tells us the proportion of the genetic makeup of an individual that's homozygous. So many of you have programs to calculate the inbreeding coefficient, right? Computer programs, you can get them, they're easy to get, and you can calculate the inbreeding coefficient. And what that number tells you is the proportion of genes, the percentage of genes that are homozygous. That's all it tells you. So if you have an inbreeding coefficient of 0.3, 30% of the genes in that dog are homozygous. And that's exactly what it tells you, and that's the only thing it tells you. For example, an inbreeding coefficient of 30 means that 30% of the genetic makeup of that individual is homozygous, and the balance, 70% of that individual is heterozygous, has mixed genes, mixed pairs. Heterozygous means that an individual gene or pair of alleles are different. Big A, little a, the first gene is a big A, and the second one a little a, or a little a, big A, either way. It says that heterozygous says the genes are different. Other terms for heterozygous are carriers. You've heard the term carrier, or factored. is another term that they use. It means exactly the same thing as in collies, a sable that carries for the blue gene, or they'll say a blue factored sable. And it says that they carry one gene. Some people do not like to use the term inbreeding, so they use the term line breeding. Now, most of you line breed, right? Okay. You're inbreeding at a slower rate. All it does is slow the rate of inbreeding. Line breeding is clearly a form of inbreeding which genetically slows the development of the inbreeding coefficient, and I'll show you how that works. And among breeders, we generally use it to refer to a set of dogs which are derived to a large extent from a given dam or a given sire. So if we say we're line breeding on a sire or on a dam, on a female. And that she's in that pedigree strongly or he's in that pedigree strongly. If you inbreed by degree of relationship only, there's only one paper that I've ever been able to find on inbreeding in dogs. And that's this paper by Rayfeld, published 30 years ago, 1970. And it was the definition of relationship in a closed colony of beagles. And he bred full sib beagles and showed a fall of puppy survival from 75% to 27% between the inbreeding coefficients of 0.25 and 0.785. And don't worry what those numbers are. I'll show you what they mean in just a moment. We'll come to what these two numbers actually mean. And most of our data on inbreeding comes from agricultural animals. And there's a batch of papers, and I picked out one because it showed what I wanted to illustrate. That's why I picked it. It was Schaffner on the reaction of fowl to inbreeding in poultry science way back in 1948. And it showed a loss of 4.4% hatchability and 9 eggs per 500 days, with each 10% increase in the inbreeding coefficient. But there was no effect on body weight of the animals and no effect on egg weight at maturity. So if you have a problem with inbreeding, it does not affect the whole animal. So everything doesn't go to the dogs. And so it's correctable, and you do not expect everything to go wrong with a set of dogs, and we'll get into that further in just a second. Okay, here we have inbreeding by degree of relationship only. There was no selection involved in these inbreeding technique, in this inbreeding technique, and this is what both Rayfeld and Schaffner did. He made a mating and then bred sister to brother. The first F1, the first inbreeding, causes an inbreeding coefficient of 0.25, which was the first number that Rayfeld mentioned, right? The second one, 0.375, 0.5, 0.59, 0.67, 7.3, and the last one, 7 consecutive brother-sister matings, or 7 consecutive father-daughter matings, or 7 consecutive mother-son matings. That's a little tougher in dogs. You got to have a good mama. But and that is based on degree of relationship only, and the inbreeding coefficient is 0.785. So what Rayfeld was talking about in the decrease in puppy survival was from 1 inbreeding cross to 7 consecutive inbreeding crosses. Okay, and here's father-daughter, and you can see that the inbreeding coefficient is exactly the same. 50, 37.5, 59, 67, 73, 78. Doesn't matter if it's mother-son father-daughter, or brother-sister, the inbreeding coefficient is exactly the same for those three types of matings. Inbreeding with selection is a different group, gives a different group of results. Helen Dean King selected several lines of rats through 25 consecutive inbreeding generations, brother-sister matings, to produce what's called the Wistar rat. The animals maintain reproductive ability, and they maintain vigor, and that is the most used research rat in the whole world today. I mean, there's a ton of Wistar rats. And they're now inbred probably into the hundreds of generations, because generation time in rats is very short. It's a very short generation time. And so, so these animals have been inbred to the extent that you can cross tissues. And they recognize that one's is the same as self. So they're almost identical animals. Okay, well, how she selected was not just picking any brother and sister. She selected lines of healthy animals to breed from. And if you do it that way, if you select healthy animals and maintain good husbandry techniques, inbreeding is not detrimental or extremely detrimental. It's not. With beagles, Rayfeld, the guy that published that paper, states that inbreeding at the level of 0.186 or 375, this is two consecutive brother-sister matings, or father-daughter matings, and or mother-son, that doesn't affect viability. One of the most famous, most used shorthorn bulls ever was 0.46% inbred. Inbreeding of inherently healthy, normal animals will do no harm, according to Robinson, 1982, Genetics for Dog Breeders. Although inbreeding depression is a possibility which should not be ignored. What's inbreeding depression? Inbreeding depression is probably the result of deleterious polygenes, that is, multiple genes, which are expressed in various ways, such as a decline in birth weight, poor growth, underweight individuals, lack of interest in the opposite sex, decrease in frequency or eagerness for copulation, delayed sexual maturity, irregular heat periods, productions of litters below average size, and indifferent or poor mothers. These are husbandry techniques. You shouldn't pick these suckers for breeding, right? You shouldn't pick them for breeding. If you want to maintain interest in the opposite sex, don't pick those animals for breeding, and you will avoid the reproductive problems that develop. And it's husbandry that you must pay attention to the whole dog, what the dog is producing. You can't only inbreed forever and pick this dog, and the reason I picked this dog, it might be the only puppy in the litter. It's the litter one, and you pick that dog for breeding. You do that a few times, and you're going to start collecting genes that influence litter size. We know we can change litter size in pigs. They did that back in the 70s, actually. It used to be in the 60s, 50s, and 60s, a litter of pigs would be, 6 or 7. Now, if you don't get 11 or 12 piglets per litter, and you're a pig farmer, you go broke, because you're not producing enough. You don't produce enough offspring to make money nowadays. And they increase litter size by selective processes, and you've all heard the old saw, as useless as tits on a boar pig. Have you heard that? Okay, that's wrong. That's how they selected to increase litter size, was the number of tits on the boar. That really influenced litter size in the female. And it tickles me when I think about that, because all of my life I heard that saying, I just Okay. Yeah. Rigid selection is required to combat inbreeding depression. Inbreeding depression is a real thing. I mean, it's real. You must look at the animals you pick for breeding and make sure they're coming out of healthy litters and healthy stock, and that the females are in good reproductive health. If you inbreed, you must select healthy, vigorous animals. It's a rule. In other words, to avoid or minimize inbreeding depression, you must use good husbandry. You ought to use it anyway, right? I mean, you ought to use that anyway. Some of the breeds, for example, well, Bernese Mountain Dogs or any of the huge breeds, you know, they have lifespans of 5.5, 6.5 years, 7 years, something like that, right? And you ask them, I don't know how many I've asked, how many of you select for age, for livability when you breed your dogs? And you know what? Nobody does. Do you?
Longevity, we don't see the data, but we think of that.
Yeah, I mean, if you want long-lived dogs, long lives is an inherited characteristic. If your parents are long-lived, you're likely to be long-lived. Much better. It's an inherited characteristic, and they didn't breed for long lives. That's what I think is the problem with large dogs. You know, if you want a dog to live a long time, you breed the old ones, not the young ones. And of course, you can't make that decision. You can't make that decision to breed a bitch when she's 10, right? Maybe a few bitches you could breed when they're 10, but 90% of them you can't. And so you can't make that decision when the bitch reaches 10. So you have to look at the livability of the grandparents, of the older dogs, and then select from that population of dogs. So it can be easily done, but you got to think about that when you have a breeding program. You cannot select for type alone or for your own set of characteristics. So this is inbreeding. I don't know if you can see that. Can you see this chart? This light is okay. This is inbreeding using two different sets of circumstances. So this is inbreeding brother-sister relationship. This is the inbreeding coefficient, the thing we talked about earlier, right here. We're going down 7 generations. That's not changing. The inbreeding coefficient is going to be the same. Okay, if you're doing brother-sister matings, what we have in the first mating is 50% of the genes are from the original dam, 50% of the genes are from the original sire, right? So we cross brother and sister. Where do the genes come from? The original dam and the original sire. They'll rearrange themselves so that each puppy isn't identical, so they rearrange themselves, but we haven't introduced any new genes. So the genes are from the original dam and the original sire, and you can go down 7 generations, and if you don't introduce any stock from the outside, when you're all done, you've got all of the genes from that original set of parents. What are the ground rules for that kind of mating? Both parents had better be good, hadn't they? Because you're not introducing any new gene. And what I want you to do is think about how inbreeding influences your dogs. And you don't want to inbreed on a set of dogs like this if there's a major fault, right? Because they can't correct themselves. They don't have the genes to correct themselves. It'll stay there. You can't get rid of that fault. If you have a fault, you've got to outcross to correct it. So inbreeding is a breeding technique. It's not anything good or bad. It's one way of breeding your dogs. Okay, let's look at the other one. Father-daughter matings. F1 generation, like this one, 50% of the genes are from the original dam, and 50% are from the original sire. Rebreed the sire again. Now it's 25-75. Now it's 12-87.5, down to less than 1% of the genes, 0.7% of the genes, are from the original dam. 99.2 something percent of the genes are from the sire. That sire had better be good, hadn't he? He'd better be good, because all of the genes are out of him. And that's what happens when you inbreed. So if he's got a major fault, every one of them suckers are going to have it, right? And not only that, he's has an inbreeding coefficient of 78%. All of the genes are his, and all of the genes are paired. What are the puppies going to look like? They're going to look like him. They have to look like him. There's no other way for them to look. And so that's the influence of inbreeding. That's what happens to you when you inbreed. This guy had really better be a super dog, or you shouldn't do this. Then there's Wright's coefficient of inbreeding. I'm going to go quickly here. Here it is. There's the formula up there. Here's how you calculate it. But I don't ever do that. I use this table here. So you can look it up. You can look it up, and you don't need to do all the calculations. If you got it on your computer, go ahead with the computer, because the computer does all the work. And there's nothing wrong with that. But I look it up. I can use that formula, but it's a pain in the tail, actually. In the most severe inbreeding situation possible, parent to offspring or brother to sister, the risk of disease caused by inbreeding is, for one specific gene, this is one gene. If you have a parent to offspring, the risk of a defective, each puppy in the litter has a 12.5% risk of being defective. 87% chance they will not be defective from one gene. Brother and sister matings is 6.25%, but there are two common ancestors, so it doubles the risk. And a brother-sister mating, full brother-sister mating, is 12.5%, exactly the same as the parents, the risk of producing a defect. Half brother to half sister is just half of that, 6.25%. First cousins, 1.5%. Second cousins, 0.37% is the specific risk. In us, in humans, the reason we passed a law about inbreeding is that in the mating situations that we're in a random mate. We are legally randomly mated, because in most states you can't marry closer than second cousins, and in a few states first cousins. And the reason for that law is that there's a 33-fold difference between this number and this number. It's 33 times higher. So there is a legitimate reason, statistically, for not inbreeding among us. And we have another problem, of course, and that is religious and ethical problems with mating with your daughter or your sister. And those problems are real to us because we set up the ground rules for that. You know, what's moral? We set up what's moral for ourselves. But to tell you the truth, I've never found a dog that really cared. How many of you found a dog that really cared, you know? And they don't have the same moral hang-ups that we do they? I'm not telling you to inbreed with your mother or your sister or your father or anybody. I'm telling you this is what the risk is, and the moral aspects of it that we have for ourselves do not apply to our dogs. And most people that talk about inbreeding aren't talking about this factor, they're talking about the moral factor, you know? Oh, should I let that dog breed a sister? Why not? I mean, they don't care. And the question that you want is what kind of puppies you're going to get. That's the question. Okay. Now we're talking about for one gene. Okay. The risk for recessive disease for each puppy in the litter as a result of any 5 genes is 45%. There's a 45% chance that each puppy in the litter will have an abnormality for 5 genes. What your survey tells me is that 46% of the dogs that you produce right now are defective. 46.9%, in fact. You are already above this figure. Right? So if you inbreed, you're not going to do anything worse than you're already doing. That's the facts. And most people, when they look at inbreeding, say that this number is high, and the number for your breed is not much different than it is for any of the other 8 breeds that we have that kind of information on. Most breeds of dogs, we don't have an idea of the frequency of disease. There's only a few clubs that have really done the kind of a survey that you can analyze the data in a productive way. And when you look at them, there's not a big difference between the 8 or 9 breeds, however many I'll show them to you in the next lecture. So this problem is no worse than you're already doing. It's just the way it is. For those breeds that we have some reasonable estimate of the frequency of genetic disease, general risk for genetic disease in Cairns, Scotties, Bichons, Newfoundlands, Bernese Mountain Dogs, White Shepherds, and Westies, 33, 40, 68, 66, 29, 33, 40%. Not a big difference. You know, you're 46, so you're kind of right in the middle of this group, right? As you can see, the general risk for genetic disease in a breed of dogs is not much different from the risk of producing genetic disease from the severest form of inbreeding, considering any 5 genes carried by that family. Not much difference. Keep in mind, the high risk of genetic disease which we see in dogs is not caused by inbreeding. I mean, the fact that you have 46% of the defects in your breed is not caused by inbreeding. Inbreeding does not cause mutations. What causes a gene to stay in a breed is outcrossing. It's outcrossing that does that. It's caused by outcrossing, by matadors. And a matador is a dog that produces those very good dogs that are used extensively, because they produce good offspring. I mean, you don't breed a dog a lot of times if that sucker's ugly, right? You breed a dog a lot of times if he's a good dog. That's how you get a lot of matings. So the high risk of genetic disease in dogs is caused by the breeding method that they tell you to use to avoid the use of inbreeding, which causes genetic disease. That's stupid, isn't it? I mean, they're telling you to spread disease when you outcross. That's what they're telling you to do. And that is what you do when you outcross. If you inbreed, you keep a genetic disease within the family. If you outcross, you spread it. If you hear people talk about inbreeding, they talk about inbreeding as if you're spreading the disease, and you're not. You inbreed, you keep it in the family. Okay, seems silly to me. The problem we have in our genetic thinking about dogs is we anthropomorphize. Now that means we think of our dogs like ourselves, right? We're not dogs. We try to give dogs our morals. We can't do that. Dogs don't care. We try to apply what's true in humans to dogs, and we can't do that. People are legally outcrossed. We are. We are legally forced into random matings. If you stop to think about that, folks, that's the way it works. Dogs are not legally outcrossed. There are no matadors in people. Matadors are common in dogs. It's common in breeds of dog. In some breeds of dogs, one male may have 200 or 300 or 400 matings. And if you take a Labrador that we know at least carried for PRA, he had 300 matings. I think it was 300 matings, and produced with 300 times 7, 2,100 puppies. Half of which, for sure, at least half of which are carriers for PRA. And if he was affected, all 2,100 are carriers. Genetic disease is rare in humans, and it's common in the dog. Genetic disease is common in dogs. 46% of your dogs have a genetic disease, at least one. And that makes it common in my book. We do not breed humans for specific purposes. Dogs are purpose-bred. And if they do not fulfill the purpose that we have for that dog, we have a strong tendency to dump them, don't we? If we want a dog to win in a conformation show, and he goes to 8 shows and doesn't win a point, what are you going to do with the dog? Keep him? You might keep him, but most people start trying to find a home for him so you can get a dog that wins. I mean, that's the way we do it. We breed dogs for purpose. Maybe we don't want to use them for conformation. Maybe we want to use them for agility, or maybe we want to use them for hunting. I don't care what choices, specific choices you make, but you get dogs for a purpose, and you want the dog to fulfill that purpose. And if he doesn't fulfill that purpose, you dump the dog. That's the way it works. We talk about inbreeding like it lasts forever. Like once you inbreed, it's forever. It takes 14 years to go from F1 to F8. Here we go. First generation, 2 years. The second generation, a generation is the time it takes from a dog to go from birth to reproduction. Generally speaking, it's at least 2 years. That's a fast generation in dogs. A fast generation. So we got 2 years, 4 years, 6 years, 8 years, 10 years, 12 years, 14 years. This is F7, not F8. 14 years to go from generation 1 to generation 7. That's a long time. How long does it take to get back? To get back to 1. How many matings? Anybody tell you?
4.
How long does it take to get back to the original parent status? It takes 1 outcross. 1 outcross, and the animal's heterozygous again. You're right back where you started. So no matter what happens to you, if you inbreed and you don't like what you're getting, outcross right back where you started. That's the way it works. That's real. And people talk about inbreeding like it's going to last forever. If they say that, you know they don't know what they're talking about, because 1 outcross does it. You go from here all the way back to here in 1 breeding. Breed F8 should be F7 to an outcross, and the offspring are back to the original parent status. I don't know how I got to F8 in here, but I did. They're outcrossed. So we have covered 2 of the main points against inbreeding. One was the risk of disease, which we just talked about here, and the other one is the inbreeding coefficient. inbreeding depression and disease caused by the frequency of defective genes among relatives. And the third point that's often made is the lack of adaptability, which is caused by homozygosity. Theoretically, if most of your genes are heterozygous, that is, you have one gene which is recessive and one gene which is dominant in a characteristic, theoretically, an individual that's all heterozygous has more adaptability, right? They have more adaptability because they can change easier than an animal that has all its genes paired, or most of its genes paired. That's the final argument. That is, since both alleles are identical, the animal must be less adaptable genetically. That's the theory. And as far as I'm concerned, you can make up your own mind about that. But I believe dogs have been proven to be the most adaptable species on Earth. We can start with any set of dogs that we have. If you want to start with a Labrador and cross it with a St. Bernard, we can come up with a new breed. And we can make that dog look alike. I mean, you guys are creating a breed right now. That's what you're doing. You know, you're forming the nucleus and adding to it the characteristics that you want your dogs to look at when they end. After all, there are at least 308 breeds in the U.S. and 500 in the world, and there's no other species on Earth like that. We can take a 2-pound Chihuahua and breed it to a 200-pound whatever, St. Bernard or Matador or Mastiff, and we'll get puppies, right? If you happen to do that, folks, make sure the female is the Mastiff. Otherwise, that would be not a good cross. I believe that inbreeding is neither good nor bad. Used correctly, it will do what you want it to do. And used incorrectly, like also occurs with outcrossing, it'll mess up your breeding program. Now, you can outcross and mess your breeding program up, and you can inbreed and mess it up. Any questions about inbreeding? Good, because now we'll go on to Shiloh Shepherds. How this breed ends up fixed as a breed will be influenced strongly by inbreeding. And if you don't inbreed, folks, you will never have a breed that reproduces itself. Okay, genetic diseases of the Shiloh Shepherd. This is based on the Shiloh Shepherd Dog Club of America survey, which went from January 1st, 1991 to January 1st, 2000, or December 31st, 1999, whichever you like. The survey was conducted by the Genetics Task Force of the Shiloh Shepherd Dog Club of America, which included these individuals. And the survey was assembled by these individuals. You can see they're all members of the group. I met several of them today, and I enjoyed it. The data were collected by Steve Betcher and were compiled by Karen, and she sent the data to me for analysis. I had nothing to do with the survey except to talk about the survey before it was sent out to you, and then to analyze the data after it came to me in a compiled form. You can thank Karen because I had her going back to the computer several times, and I appreciate it because she got me the answers fast, and we had a relatively short period of time between the end of the survey and this talk. We were kind of close together. There were 356 total dogs in the survey, of which 167, or 46.9%, had at least one genetic disease. 189, or 53.1%, reported had no genetic disease. This number is as important as this number for you to figure out what's happening to you. So, 46.9% of all Shiloh shepherds had a genetic disease of one kind or another during the survey period. Is this survey perfect? No, surveys are never perfect. Is that number exact? I don't know if it is or not. I can't tell. But I can tell you it's probably the best number that you have for disease in Shiloh shepherds. It's better than a wild guess. And it may not be exact, but I think it's pretty good because that 359 dogs, or 56 dogs, makes up about a third of your total population that was available for this survey. And I don't think any other breed that I had listed there had 1/3 of their dogs involved in the survey. I think this is a very good record, and I think it's a good survey. I would like it to have been more, but it, I mean, I'm happy with what we got. There's no reason to suspect that this survey is different from all other surveys, but it's a very reasonable estimate, as far as I'm concerned, of the current disease situation in Shiloh shepherds. This survey is recent. It's what's happening to you right now. And there's no better information available on diseases in Shiloh shepherds anywhere that I'm aware of. Let's look at the Shiloh shepherd survey data. That's kind of a tongue twister there. Shiloh shepherd survey. In the alimentary system, we've got 7 diseases: megaesophagus, the small intestinal bacterial overgrowth syndrome, Pachygyria enteropathy, canine sprue, bloat torsion, idiopathic canine colitis, and perianal fistulas. The mode of inheritance for all 7 of these traits has not been determined. We know they're genetic. We don't know how they're inherited. And the frequency of the disease is this is the number of dogs per 100. So you have 0.6% of the dogs have this disease. 7.9% of your dogs had small intestinal bacterial overgrowth syndrome. 3.6% of the dogs, percent of the dogs had bloat or torsion, and 3.1% of the dogs had idiopathic canine colitis. Behavioral diseases, you have aggression among your dogs. Not a huge percentage, 1.4%. Hypothyroidism, Addison's disease, mitral valve defect of pulmonic stenosis, subaortic stenosis, and patent ductus arteriosus. In the immune system, we have selective IgA deficiency, demodicosis, and systemic lupus erythematosus. We have pancreatic hypoplasia, or extrapancreatic insufficiency, same disease. Different name, same disease. In the integumentary system, we have acromutilation syndrome, contact dermatitis, German Shepherd dog foot pad syndrome, idiopathic onchomedesis, pemphigus vulgaris, sebaceous adenitis, systemic lupoid onchodystrophy, and umbilical hernia. This name is toenail disease. You have epilepsy, or glycogen storage disease, and spinal muscular atrophy in the neurologic system. In the ocular system, keratoconjunctivitis sicca, dry eye, cataracts, and corneal dystrophy. Pardon? Wasn't listed. Cryptorchidism, and in the urinary system, uroliths. In the skeletal system, cleft lip and palate, hypertrophic osteodystrophy, osteochondritis dissecans, OCD, FCP, non-fusion of the anconeus, panosteitis, or fracture. This another name for this is fractured anconeal process. premature closure of the ulna, spina bifida, imperfect dentition, mostly missing teeth, overshot, undershot, and hip dysplasia. Now we're gonna go over these several more times, but I'm going to add different information each time we go over the set of diseases. And we will use this chart, and you have it in your handout. This chart was included in the handout with one more column that I'll get to in just a moment. Before we get into the data, how I'm going to analyze this data, we need to go into a little background. I'm going to present the frequency of the various diseases in Shiloh shepherds based on the survey results that were given to me. And from this data, I'm going to calculate the frequency of carriers. How many carriers are in the general population? Or I'm going to calculate the gene frequency, is another term for it, in the general population of Shiloh shepherds. In other words, to have a genetic disease floating around in your company, there must be carriers, hidden carriers, in the population of dogs, and when they're crossed, disease pops up. And since it's generally the policy of breeders not to talk about affected dogs or to lie about affected dogs or to avoid talking about affected dogs, or if you want to be nice, prevaricate about affected dogs, we're just not used to talking about disease. If we want to do anything about it, we have to talk about disease, and I'll show you why as we go through the seminar. That's the basis of the seminar. What do you do about disease? In order to calculate the frequency of carriers, I'm going to use a thing called the Hardy-Weinberg law. Another name for it is the Hardy-Weinberg equilibrium. Basically, the law states that in a population in equilibrium, that is a set of dogs that are static in the sense of numbers, which is randomly mated, the frequency of a gene is the square root of the frequency of the homozygote. So it's the square root of the frequency of the affected dogs, the number of affected dogs that you have for that gene, the homozygotes for that gene. Okay, the formula is a squared 2ab, b squared. The law was designed for autosomal recessive traits. That's what it was designed for. It can be used with accuracy on autosomal dominant traits and with sex-linked traits. And you don't even need to use it on autosomal dominant traits because a dominant gene shows itself. So you don't have to calculate anything. If you like to calculate, you can calculate it anyway. You get the same number. But for the gene frequency of a dominant trait, you just count the affected dogs, and that gives you the gene frequency. It cannot be used on polygenic traits because with polygenic traits, more than one gene is involved. So you cannot use it. It cannot be used on any trait for which the mode of inheritance is unknown, right? So in that first set of small intestinal diseases, we don't know the mode of inheritance of any of them. So we can't use this, right? Although I know it's not perfect, I'm going to use this law anyway in order to guesstimate carrier frequency. I'm a bad boy, okay? But I want you to understand the ground rules for the Hardy-Weinberg law. I don't want to try to pull anything over your eyes. What actually happens if you use the Hardy-Weinberg law on a polygenic trait is you calculate the minimum number of genes that's present in the population. You're calculating for one gene. If there's more than one gene, that number is higher, not lower. So I give you a guesstimate of the minimum gene frequency. And if it's unknown, then, if it's unknown, it's either sex-linked, it's recessive, or it's polygenic, or it's dominant. And for three of them, the law works. For the fourth one, it's polygenic, and you get the minimum number. okay? So the number of genes here is real, although it may be lower than what's real for any given disease that we talk about. It will not be higher, or I mean, it will not be lower than that, but it can be higher. You can get a higher number. You as a breeder need to know carrier frequency in order to make breeding decisions for your dog. If you're going to decide whether to breed this dog or not breed this dog, then you need to know the frequency of that gene in the general population. And if you know the risk in your dog is 12.5%, and the risk in the breed as a whole is 25%, should you breed your dog? Of course. If you breed any other dog, you're going to have a higher risk. And that's why it's important to look at it, and that's why it's important to have this survey. As far as I can see, there's no other way to do this except to do through the Hardy-Weinberg law. Same list of disease, so I'm not going to go through them again, but I am going to show you this side. There's a new column now, and this new column is the guesstimate of carrier frequency. So for megaesophagus, 0.6% of the dog are affected. In order to get that, 14% of your dogs must be carriers. It's a minimum number. With the small intestinal bacterial overgrowth syndrome, 7.9 dogs out of 100 have that disease. 40% of the dogs in the general population must be carriers to produce 7.9%. How can I talk about this as if it's a random mating system? Because you don't turn your dogs loose in the park to randomly mate them, do you? No. But how many of you really know the genetic makeup of any dog in the breed? I bet nobody. So as far as disease is concerned, no matter what you say, how you breed your dogs, you're randomly mating because you cannot make specific selection to avoid disease. Why? Because you don't know where the genes are. Most of you really don't discuss dogs that have disease. Is that bad? Yeah, I think it's bad. But I also think it's what you've been trained to do, because dog breeders have been doing that for 100 years. You know, we're just starting to look at genetic disease from a real standpoint. I'm not exactly sure. Most breeds I can say when I come, you wouldn't have invited me here 20 years ago, because 20 years ago they weren't ready to accept even what we're doing here. People weren't ready to accept disease as a problem that we can challenge and solve today. You know, it's nice that we have a DNA test, and I approve of that, and I strongly support research on locating specific genes. But if we wait for that to happen, if there are 500 genetic diseases and it costs $100,000 to find a gene, and that's the number that they toss around, you need $50 million, right? $50 million. Right now, we're spending about $1 million a year on locating genes, approximately $1 million a year. Any way you figure it, that's 50 years, right? Can't happen tomorrow. And if one researcher can find one genetic disease gene every 6 months, and he can find that means 2 a year, it's going to be 250 years to get through the 500 diseases. And if there are 10 guys doing that at the same rate, it's going to be 25 years. It's not going to happen tomorrow. It's not. And in addition, a lot of our major diseases are polygenic, like hip dysplasia, like portocable shunts, like elbow dysplasia. These are all polygenic. In human research, we spend over $100 million a year on the Human Genome Project, $100 million a year. We've not identified one single polygenic trait in people yet. So we're going to find a cure for hip dysplasia, on less than $1 million a year? I don't think so. I mean, that's my bet. I hope they do. I mean, I really would like that because it would solve a lot of problems. But my bet is they're not going to do that. And I bet a lot of money, and I told them, don't waste your money. That's the way it is. Okay, so here we're at 28 diseases. We've done the same thing right down the list, and these numbers, we'll get to how we use these numbers in just a minute, but these numbers are the same. I've added that column, the frequency of carriers in the general population, and that's a minimum number, and we have the whole 46 diseases. Okay, that number adds up to 803.5. Divide that by 100, and every Shiloh shepherd, on the average, carries 8 defective genes. No way around it, right? If the diseases are right, and the frequency is anywhere near right, this is near right. That's the way it is. Every Shiloh shepherd carries 8 defective genes. Now I can look around the audience here, and I can see a lot of you guys are genetically defective. You know that? I can. You're genetically defective. You're wearing glasses. I am. I wear glasses. You wear glasses. You know, if you wear glasses, most of our eye defects in people are genetic too, just like they are in your dogs. I also happen to have diabetes, the inherited form of diabetes. So I personally have at least 2 genetic diseases. I may have others that I don't know about yet. Yeah, I really don't want to find another one. If I do, I'm going to say, damn. Man, I wish that hadn't happened. So 46.9% of all Shiloh shepherds are born with or develop a genetic disease during their lifetime. And on average, there are 8 defective genes present in each Shiloh shepherd. What do you think? 46.9% of all Shiloh shepherds have a defect, and 8 defective genes per Shiloh per dog. Are Shiloh shepherds bad dogs? No, at least not in my opinion. I mean, Shiloh shepherds, like all living things, are mutable. We have mutations. Shiloh shepherds have mutations. Labradors do. Trees do. Elephants do. Everything. Every living species has mutations of the DNA. It just happens. And most of the mutations that occur during the reproductive process. So if you think you're going to, with some breeds, you can't do it in your breeds because it started here, but if you think you're going to, if you want to get an Afghan hound and you want to go to Afghanistan to get your Afghan hound, and you think you're going to get a genetically normal dog because all of the things that cause mutations aren't present in Afghans that we have in the United States, you're crazy. 60% of the mutations are caused by reproduction. So if they're not reproducing their dogs, then they won't have those mutations, but you won't have any dogs to buy either. You know, there's no way around that. As a result of the fact that mutations occur over a period of time, they tend to accumulate in a breed. And Shiloh shepherds are no worse than you or I. On average, each one of us carries 3 to 5 lethal equivalents. Now, a lethal equivalent is the amount of defective genetic material that kills at birth. So I have diabetes. That should shorten my lifetime about 8 to 10 years. So that's like 12% of a lethal equivalent. Okay? And if my eyes don't get bad enough so I step out in front of a semi, that may not be a lethal, may not even count. Defective eye genes may not count in lethal equivalents. So what that really tells us is that most of us have maybe 20 to 25 defective genes. In a random mating system like we have here, we don't see many genetic diseases. The other thing is most of us don't have enough puppies, kids, to really expose the genetic diseases that we have. If you only have one offspring or two kids, and you and your husband carry for the same gene, I mean, you're going to have less than a 50-50 chance of both of those showing up. There's only a 25% chance that one of those kids will in fact show the defect. If we have enough information on other breeds, it turns out that they're pretty much like Shiloh Shepherds. Let's look at that same set of dogs again. Number of diseases for Scottish Terriers, 41. The Cairn Terriers, 46. Bichon Frise, 47. Newfoundlands, 50. 52 Bernese Mountain Dogs. 57 in White Shepherds. PBGVs have 49. And you guys have 46. That's not bad, is it? No, I mean, I'm not telling you it's good. I don't think it's good either. But it's not much different than other dogs. So you are not bad people because your dogs have 46 genetic diseases. I mean, that doesn't make you a bad person. And it doesn't make you a bad dog club. It just isn't that way. But we can do better than this. We really can, you know. And the frequency of affected dogs in Scottish Terriers, 33%, 40%, 29%, 66%, 68%, 40%, 58%, and 46%. You're not much different than those guys. Okay. And the number of defective genes per dog, 4.75, 4.6, 4.5, 10.2, 7.1, 7.9, and 8. Why is your number higher when the number here is lower and the frequency is kind of in the middle? Because the curve for calculating the number of carriers is not a straight line. So the lower the number of animals affected with a given disease, the higher the frequency, the higher the number of genes must be in the general population, so that there in fact is going to be a mating that'll show that disease. So you'll see when we get to another table, you'll see how that works. It's not a straight line. So you have a lot of diseases, but a low frequency of a lot of those diseases. Like there was one affected dog or two affected dogs. Remember that, Karen? In the whole population. And so that causes the number of genes to be higher because it's not a straight line. Why is it like that? Why are all of these breeds have affected dogs? And that question is easy to answer. It's because nobody does anything about genetic disease. I mean, that's the facts. Let's look really at what we do as a club to control genetic disease. Some individual breeders I know make strong efforts to control genetic disease, but they'll work on the one or two diseases that they know about. Most breeders don't follow their dogs long enough to make sure the defects that are produced by their own dogs. Some are very meticulous about it, but if you don't follow your puppies, you cannot know the genetic makeup of the parents. You must follow the puppies. And remember, it's not the job of the buyer to call you up. That's your job. It's your job to follow your puppies if you want to breed healthy dogs. And if you set the system up, that works out pretty easily. You know, I mean, some people don't like to call their breeders and give them bad news. You know, they really don't. So if you don't call, you're not going to find out. In many cases, some of them will. And I know that most purchasers of dogs, because I've talked to a lot of them, in my position, I mean, you hear bitches about defective dogs. Somebody's always telling me, you're a geneticist. Why don't you do something about it? And my problem is I'm not the breeder. I'm not the breeder. But if you approach them and you tell them when they buy a puppy, look, I'm going to call you in a year. I'm going to call you to give them a period of time. If you move, would you please send me your phone number? And the reason I'm going to call you is if I want to breed healthy dogs, I must know what diseases are in my dog, and I have to find out if something's wrong. And you know what? They like that. They think you are an ethical person. And the fact is, you are. Because if you cannot prevent a disease that you don't know about, you just can't. Over the years, there's been literally no effort to control genetic disease in purebred dogs. Not just Shiloh Shepherds. The same is true for nearly all breeds of dogs. There are a few exceptions. Alaskan Malamutes controlled a disease called Malamute dwarfism. That was a disease that had a frequency of about 12% at one time in that breed, and now has a frequency as a result of a coordinated program by the club. It now has a frequency of less than 1%. The Inland Empire Collie Club reduced the frequency of collie eye disease from something like 70% to less than 55% in 5 years. They dropped the frequency of that disease 20% in 5 years. Portuguese Water Dog Club got rid of a disease called a storage disease. It's a gangliosidosis. That disease is gone now. Miniature Schnauzer Club reduced the frequency of juvenile cataracts from about 5% to less than 1% in 4 years. And boxers got rid of a disease called boxer axonopathy, and it's a disease in which the nerve impulses travel incorrectly, and so the dogs have severe ataxia, usually ending up in total forelimb paralysis. That disease is not present in American boxers, the last report that I heard. It's a disease that's been limited to England. It's lucky, because we import boxers from England, we're going to be lucky if the disease does not show up here. Because they did something about it, but for a long time they sold us dogs. You can control genetic disease. These clubs have proven that, but it doesn't just happen. Mother Nature won't do it for you, right? Mother Nature doesn't have a darn thing to do with breeding purebred dogs. And when we don't turn them loose in the park, we decide who they're going to breed. You do it. If you want something to happen, you have to do it as breeders, or it won't get done. If you don't control genetic disease, nothing can happen. Well, the fact is you've already started. Excuse me. This survey is the start. Tells you how serious the problem is. 46.9% of all the dogs you produce have a genetic defect. Although 6 out of those 46 diseases might reasonably be called false rather than disease, if you looked at the list. For example, hypothyroidism, umbilical hernia, cryptorchidism, imperfect dentition, overshot and undershot. I mean, you might want to call them false rather than diseases. And if you want to call them false, I don't have a problem with that. That's perfectly all right. If we take these faults or disorders into consideration, then the frequency of real diseases is 33%, and the number of defective genes per dog comes to 6.8 instead of 8. However, the reason I listed these faults in this report is that most breeders think of them as serious, and the reason that they think of them as serious is you can see all but one of them. The only one you can't see is hypothyroidism. You can see imperfect dentition, you can see overshot, you can see undershot, right? And once you can see it, people don't like it because you can't hide it anymore unless you correct the trait. And I'm not sure about the ground rules in your breed, but if you happen to be a member of the AKC and you correct a trait, with the exception of umbilical hernia, you can now correct umbilical hernia and show the dog. But if you correct a trait and show the dog, they'll toss your can out. You're gone, right? And why they made it legal to correct umbilical hernia and didn't make it legal to correct inguinal hernia, when the mode of inheritance is probably the same for both of them, different genes, but the same mode of inheritance, I mean, that's borderline stupid. I mean, that's my opinion. You know. So what we tend to do is worry about what we can see more than we worry about disease you can't see. Like you can't see hip dysplasia unless you take a radiograph. And as far as I'm concerned, hip dysplasia is a far more serious concern than any of those faults. But we tend to take care of the faults because you can see them, and worry about the faults because you can see them, and we don't worry about the diseases that we should be worried about. My idea of serious disease is, one, a disease that hurts the dog. Number two is a disease that makes the dog non-functional. You know, a dog that goes blind is non-functional, even though he'll get along in your home. He won't be able to do the job you want him to do. Or a disease that causes serious concern to the purchasers. Like if you sell a dog that develops portal cable shunt, you sold a person a dog for whatever you sell your dogs for, $500 or whatever it is, and then you've handed them a bill for about $1,200 to $1,600 for the surgery to correct the portal cable shunt. And that's not good. I mean, people are getting to look at dog breeders like they used to look at used car salesmen, right? Are you selling me a defective product? And I think they have a right to do that. I mean, I don't think that we've treated our purchasers well in many cases. Many breeders will replace a defective dog without argument. Others don't do that. And I get involved in a lot of cases like that. And I'll tell you the truth, I'm always on the side of the purchaser. I always take the purchaser's side. Unless you've done the right thing. If you've done the right thing, then I will in fact be on your side. And the right thing is to tell a purchaser what the risks are when you sell your dog. That's the right thing. Yeah. Let's back up. I need to. If this survey is a start, how does it help us? Several ways, if we're willing to do what needs to be done. We need to identify the dogs that have genetic diseases. We need an open registry. We need an open registry. It's very difficult, if not impossible, to proceed without the knowledge. We must know where affected dogs are, and we must make that available to the public. Anybody that wants to know about the dog. If we do that correctly, and everyone does it, there'll be no shame in it. There's no shame in having a dog that has a genetic disease unless we don't try to prevent it. I mean, that mutations happen, folks, and they happen to all of us. I happen to have two defects. I'm not pissed off at my parents because I have diabetes. They didn't know. You know, I turned diabetic 55 years after I was born. You know, Jesus, not there. You know, I mean, they didn't know. So, you know, there's no blame associated with it unless we fail to take the steps that we take once we know what's happening to our dogs. That's where the problem comes in, as far as I'm concerned. That's where you're ethical or not ethical. Why? The why, of course, is easy to answer. Knowledge about affected dogs tells you where the defective genes are. If you know what dog has the defect, you can tell every dog in the whole pedigree that's a carrier. And you can go back 6 generations and forward 6 generations, and you can assign a risk to every dog directly. Knowledge about phenotypically normal dogs tells you nothing about the genotype, whether the animal is a carrier or not. I have great arguments and continual arguments with OFA. I think OFA is a great phenotype diagnostic tool. It tells you the phenotype of the dog. It does not tell you whether that dog is breedable or not, because it does not tell you the genotype. It's a polygenic trait, and the way you control a polygenic trait is by progeny testing. Every breeder knows how to control how to control polygenic traits. You just don't apply it to hip dysplasia. You know, if I asked you to correct a top line on a dog, you know, you have a bitch that has a top line that you don't like. You need to correct that. Nearly every one of them will tell you what you do is you look at the dog you want to breed. He's got to have the right top line. You look at his parents, and you look at his litter mates, and you look at his offspring to tell the genetic makeup of the dog. Is that dog going to be able to correct the top line? And when you approach it, that's what you do. But for some reason, you listen to those nutty people, you know, veterinarians for one, that say, take a picture of that dog and then make your breeding decision based on one picture. And all of the litter mates of that dog may have hip dysplasia, and he's normal. The only one in the litter that's normal. And you pick that animal as the breeding animal, and that's crazy. You never would breed your dogs that way if you're breeding for a conformation problem. And why you do that with OFA, I don't know. And why you do it with pin hip, those are 2 of a pair. Neither one of them will have an open registry. And on top of that, OFA, if you have a dog with good hips and bad elbows, they'll tell you about the good hips and won't tell you about the bad elbows, and you're breeding to that dog. They won't do that. And you know, I think that, I don't think that's very nice. And believe me, I know those guys, and I tell them. They don't like me, actually, all that much, but knowledge about the phenotypically normal dogs, like dogs with an OFA, tells you nothing about the genotype if you base it on that one animal. And so if we look at a table here, this is the risk of being a carrier if you're related to an affected dog, right? So if your dog is related to an affected dog, and it's a parent or progeny of an affected dog, there's a 100% chance that that dog is a carrier. 100%. If it's a litter mate, a full brother or sister of an affected dog, the risk is 66%. If it's a grandparent, aunts, uncles, and half brothers and sisters, there's a 50% risk. If it's a nephew, niece or nephew, 33% risk. Great-grandparent, cousins, half aunts and uncles, great-grandchildren, 25% risk. Great-great-grandparents, first cousin, once removed, and second cousin, 12.5% risk. And great-great-great-grandparents, first cousins, twice removed, and third cousins, 6.25% chance. This is an empiric risk. It's recognized by the courts. It's recognized in human genetic relationships, lawsuits, as real. And it also applies to dogs. And it would be recognized in court if you go to court over an issue. This is, in fact, the risk that you have if your dog is related to an affected dog in any of these ways.